This conference will now be recorded.
Hello everyone. Last day we have started group 17. Okay. After this there will be group 18, but some portion is left. Today we will start with preparation of chlorine, then properties of chlorine. After that, another important compound of chlorine, which is HCl. How to make HCl and what are the chemical properties and what are the application of HCl, that we will see, and some related problems. And after that there will be discussion about group 18. Preparation of chlorine. By heating manganese dioxide MnO2 with concentrated HCl, it is possible to produce chlorine. Okay, so this is the main desert product and these are the side products. But if it is in the laboratory, then another method is also possible, which is salt of chloride and strong acid. It can be used in place of hydrochloric acid. So now we have taken NaCl, not HCl. In the previous reaction, we have taken HCl, but now it is NaCl. And instead of taking HCl, there is also a strong acid, which is H2SO4 and MnO2. So MnO2 is still there, but instead of HCl, now it is NaCl and H2SO4. So here also we are getting chlorine. Okay, so these two are the methods for generation of chlorine. Now there is a third method, which is electrolytic process. We can acquire this gas, that is chlorine gas, by the electrolysis of concentrated aqueous solution of NaCl. Now aqueous solution of NaCl, when it is saturated, it is known as brine, and a particular cell named Nelson cell is used here. In this case, at anode chlorine is produced. At anode there is oxidation reduction going on. That means Cl minus, that will be converted to chlorine and electron is removed. So chloride, there is -1 charge and it is losing electron. That means this is oxidation. So chlorine will be produced at anode. So this is the reaction which is occurring at anode. This is the least expensive technique and it also gives purest form of the gas. So overall reaction, if we see, this is the reaction which is occurring at anode, but if we consider overall reaction, then it is this one, that is concentrated NaCl, which is brine solution. Water is also there, and ultimately the products that we are getting, sodium hydroxide, hydrogen gas and chlorine. So this is our main desired product. Fine. And in this case we can get purest form of the gas. The reason is, if you consider the previous two reactions, here some undesired products are also there, and we have to remove that to get pure chlorine. Here also NaOH is there, but this is gaseous in nature, so it can be removed easily, and hydrogen is also gaseous. So here purification process will be easy, and impurities, that is to remove chlorine from impurities, that will be easier. So that is why it is least expensive as well as purest form of the gas. So this method is good for preparation of chlorine. Then the fourth process, chlorine is manufactured by the oxidation of hydrochloric acid in presence of CuCl2, and this reaction, this process is known as Jacobs process. Temperature is high, 723 Kelvin. Pressure is 1 atmosphere. So the equation that is involved here, 4HCl plus O2, it is producing 2 water molecule and 2 chlorine molecule. Okay, so this is the Jacobs process, and here oxidation of HCl, that means oxidation state of chlorine in HCl is -1, and oxygen is the oxidizing agent, but after reaction oxidation state is 0. That means from -1 to 0, this is actually oxidation. So is there any doubt in all these processes for preparation of chlorine? Any doubt? Physical properties of chlorine. It is yellow-green colored, pungent smelling. So there is a specific smell present, and it is also toxic gas. If we compare its heaviness, that is compared to air, it is 2 to 5 times heavier. It can give chlorine water because it is soluble in water. So if you are passing this gas, this is the gas. If you are passing this gas through water, then there will be generation of chlorine water. For chlorine, there are two isotopes possible. One is 37 chlorine, another one is 35 chlorine. Now, what is the definition of isotope? Having same atomic number, but neutron number is different. And that is why mass number is also different. Because proton number plus neutron number, these two together will give us the mass number. But proton number is fixed because it is isotope, and that is 17 atomic number of chlorine. But neutron number is different, so that is why mass may be 37 or it may be 35. Two possibilities are there. On liquefaction, it gives yellow liquid, and boiling point is 34.6 degrees centigrade. Okay, so it is very, very low, and as boiling point is this, so melting point must be further lower than this. So it is minus 101.1 degree centigrade. So these are the physical properties of chlorine. After physical properties, next we have to know chemical properties. Now in this box you can see it is reacting with ammonia, but these two reactions, there is some difference. When chlorine is reacting with ammonia and the amount of ammonia is excess compared to the amount of chlorine, in that case product is nitrogen and another product is ammonium chloride. But if it is the case that chlorine is in excess amount, not ammonia, now the products are different. So it depends on whether you have taken ammonia in excess or chlorine is excess. See here the number of moles that are reacting with specific number of chlorine. These numbers are also different. 8 moles of ammonia, 3 moles of chlorine. But in the second reaction, 1 mole of ammonia, 3 moles of chlorine. So products are different. NCl3 and 3HCl. Next, reaction with alkali. Now here also two different conditions are there. If the condition is cold and dilute alkali, that means NaOH solution which is alkali that you have taken, it must be under cold condition and it is dilute. And under this condition, if it is reacting with chlorine, products are NaCl, NaOCl, water. Now this is also disproportionation reaction. Why it is so? Because before reaction, chlorine is having oxidation state 0, but after reaction, NaCl is produced where chlorine is having -1 oxidation state, and NaOCl, here oxidation state of chlorine is +1. Now how you will be getting the oxidation number NaOCl? It is Na plus ClO minus. Now ClO minus, that is overall charge is -1. Now oxygen is having -2 charge, so chlorine must be +1. That is why one negative charge is extra. So from 0 oxidation state, it is converted to -1 as well as it is converted to +1. So that is why it is disproportionation reaction. Okay, but if NaOH solution is hot and concentrated, in that case product is different. Now the product is NaCl is again generated, that is same, but the other product is not same. Now instead of NaOCl generation, NaClO3, that is sodium chlorate, is generated. Okay, so here 0 oxidation state, now it is -1 and this is +5. So this is also one kind of disproportionation reaction. But remember, if it is cold dilute alkali, in both cases NaCl, H2O, these two are common. But if it is cold dilute alkali, the third product is NaOCl. But if it is hot and concentrated, now chlorine is having +5 oxidation state in the compound NaClO3. Okay, so is there any doubt in the chemical properties, the reactions that are shown here? Some more chemical properties. Chlorine, when it reacts with water, there is formation of HOCl and HCl. HCl is hydrochloric acid, HOCl is hypochlorous acid. Now this hypochlorous acid, it is not very stable. So as soon as it is produced, it will be breaking down and there will be production of nascent oxygen. So this is nascent oxygen, that is atomic oxygen. Now this is very highly oxidizing in nature because it is in atomic form. That means highly reactive form. So this nascent oxygen is actually responsible for the oxidizing properties of chlorine and also the bleaching property of chlorine. Okay. So chlorine is not directly responsible for the oxidizing or bleaching property. It is actually the formation of nascent oxygen which is responsible. Fine. We will see some oxidation reaction example. Ferrous sulfate H2SO4 chlorine. That means chlorine, if it is acting as oxidizing agent, it must be itself reduced. So see, after reaction, the fate of chlorine, now it is chloride, -1. And iron, before reaction, it is having oxidation state +2, but now it is +3. Ferric sulfate. This is ferrous sulfate, Fe2+ charge balanced by 2 negative charge of sulfate. But here it is ferric sulfate because sulfate is having -2 charge. So 3 sulfate means total negative charge -6. It must be balanced by +6 charge. That means 2 iron, each iron carrying +3 charge. In this way, you can find oxidation state. So in this reaction, ferrous sulfate converted to ferric sulfate, chlorine is reduced to chloride. Then sulfur dioxide, oxidation state +4, but it is oxidized by chlorine, and now SO2 is converted to H2SO4 where oxidation state is +6. So from +4 to +6, it is loss of electron. That means it is oxidation. Okay. Number 3, iodine is also oxidized by chlorine. Now after oxidation, the fate of iodine, now it is having oxidation state +5. And before reaction, it is 0. So this is also loss of electron. Then the fourth reaction, sodium sulfite. This is sulfite ion. This is sulfate ion. Here oxidation state is +4. How we will understand? It is SO3 2-, each oxygen -2, that means total negative charge -6. 2 negative charge extra, that means it must be +4. So from +4 now it is converted to +6. This is also oxidation. Okay, so all these 4 reactions are oxidation reactions example. Next we will see that it has, that is chlorine has great affinity for hydrogen atom. So that is why it can react with compounds that are containing hydrogen, and after taking this hydrogen it will be converted to HCl. So hydrogen sulfide, which is hydrogen containing compound, when it is reacting with chlorine, chlorine has affinity for hydrogen, so that is why now HCl is produced and H2S is converted to sulfur. You can also see this reaction as if it is a kind of oxidation, but another way also you can view this reaction as if it is accepting hydrogen. Why it is oxidation? Because oxidation state is -2 for sulfur, it is 0 here. So this is loss of electron. Then chlorine can directly react with hydrogen and it can produce HCl. This is also affinity for hydrogen. And the third example is hydrocarbon, C10H16. Carbon, hydrogen, these 2 elements are already present. So this is hydrocarbon. Here chlorine is, as it is having affinity for hydrogen, so here HCl is produced and 10 carbon. How it reacts with calcium hydroxide? Basically, after reaction with calcium hydroxide, there is formation of calcium oxychloride, which is also known as bleaching powder. Now, calcium hydroxide, it is also called slaked lime. If it is simply lime, the compound is calcium oxide. But when you are adding H2O to calcium oxide, there is formation of calcium hydroxide. So water plus lime, what you are getting? You are getting slaked lime. And this slaked lime, when reacting with chlorine, there is formation of calcium oxychloride, which is bleaching powder. There is also generation of calcium chloride and water. So remember, reaction of chlorine with slaked lime, it produces bleaching powder. Fine. Should I repeat any part? Application of this gas, used as disinfectant, antiseptic, then to sterilize drinking water, and that means for purification purpose it can be used, to clean swimming pools, used in the production of paper and paper products, then manufacture of dyes, drugs, organic compounds such as carbon tetrachloride, DDT, this is the structure of DDT, insecticide, and refrigerant. Okay, refrigerant, all these are chlorofluorocarbon, that is carbon, chlorine, fluorine containing compounds. As a bleaching agent in the wood pulp, cotton and textile industries, because we have already seen, because of nascent oxygen it has bleaching capacity. In the extraction of gold and platinum, and in the preparation of some poisonous gases such as phosgene, TOCl2, tear gas, CCl3NO2, and mustard gas. That is Cl, CH2, CH2S, then again CH2, CH2, CH. So this is the mustard gas. Okay. Here we have a problem. Product X and Y of the following reaction. Reaction number 1, reaction number 2. Reaction number 1, you are using cold dilute NaOH and chlorine, you are getting, sorry, it will be NaCl, not NaCl. NaCl, X and Y, water. So this is not given. We do not know what is X. In the second reaction, this is also reaction between NaOH and chlorine, but now it is hot and concentrated. Same products, but Y will be different. Okay. Remember the reactions that we have seen. I'm talking about this reaction. This one. Okay. So here you can see NaCl, water. These two produce both time, whether you have taken cold dilute alkali or hot concentrated alkali. But another product which is not different, it is NaOCl when cold dilute alkali and NaClO3 when it is hot concentrated alkali. So here the first product, that is X, it will be NaOCl. Now NaOCl as X, it is present only in option B. So if you are sure about the structure of X, you can choose this option. And also Y as it is NaClO3, that is also present, that is Y as NaClO3, that is also present only in option B. Okay, not other options. So that is why this will be the correct option. Another question, NaOH reacting with chlorine. See, this reaction is basically the same reaction, that is equation 2. That means NaCl will be generated, water will also be generated. But what is A? A is nothing but NaClO3, sodium chloride. And it is asking what is the oxidation number of chlorine atom in this particular molecule. This is NaClO3. That means Na plus ClO3 minus. So oxidation state of chlorine, if it is X, then it will be X plus 3 into minus 2 for 3 oxygen. Overall charge is minus 1. That means X will be equal to 6 minus 1. So here oxidation state is plus 5. This is the answer, plus 5. Any doubt in these two questions?
No doubt, ma'am.
Next important compound, HCl. Preparation of HCl we will see first. Laboratory method. HCl can be prepared in laboratory if we are heating NaCl and concentrated sulfuric acid. So it is just the replacement of Na with hydrogen, which is coming from H2. Now, in the first step, which is at 420 Kelvin, there will be formation of NaHSO4 and HCl. Now, H2SO4, there are two replaceable hydrogen present. That means the product that is generated, there is still one extra hydrogen which can be replaced by sodium. And this molecule is known as sodium bisulfate, or you can call sodium hydrogen sulfate. This sodium bisulfate, it is the byproduct and it is insoluble. That means you can easily separate it by filtration. Now, if you are using it, that is, if you are mixing it with more NaCl and you are warming it to higher temperature. Now, for the second step, temperature comparatively high, almost double, right? Now, another molecule of NaCl. Now, this hydrogen is also replaced by this Na, and this H and Cl, now it will produce another mole of HCl. And now sodium sulfate is soluble. That is the side product. So this is the method for generation of HCl, laboratory method. Now finally the HCl that you have obtained, you have to make it dry because it may be in moist condition. That is, some moisture will be present. So if you are trying to dry this HCl gas, what you can use? You can use concentrated H2SO4 because concentrated H2SO4, it has dehydrating property. It can attract water. You can also use P2O5, or you can use quicklime, that is calcium oxide. Sorry, what I have said. By treating it with concentrated H2SO4 only. These two you cannot use. Why? Because when you are trying to dry the HCl gas, then there will be reaction with these two compounds. But we do not want any reaction to occur. So that is why only H2SO4 can be used. So when you are using H2SO4, then moist HCl can be converted to dry HCl because the moisture that is present, that will be attracted by H2SO4. But you cannot use P2O5 and CO because these two are also water attracting agent, but are not used for drying purpose because HCl will react with these two compounds. But that is not the purpose. Our purpose is to keep HCl intact, only to remove the moisture part. So only H2SO4 is used. Okay. Next we will see its acidic property. HCl, when you have added it to water, this is water molecule. Now this hydrogen will be captured by the lone pair of oxygen. Now what you are getting H3O plus, which is known as hydronium ion. And here we also have this ball and stick model. This is H, this is Cl, and you are getting hydronium ion. This is the hydronium ion, and this is Cl minus. Okay. Now here what is happening? Basically, it is dissociation of HCl because HCl bond is broken. H is now attached with water molecule. It is forming H2O plus and Cl minus is there. Now dissociation constant for this particular reaction, it is 10 to the power 7. That means this is a very high value. Okay, that means the concentration in the product side, that is very high. So the equilibrium, it is more towards right hand side, and that is the reason it is a very good acid. Okay, that is a strong acid because of this high Ka value. So here you can see HCl, when it is added to water, there is formation of hydronium ion and also Cl minus. So whenever you are having any HCl solution, basically it will contain these two types of ion. One is hydronium ion, another one is Cl minus. So it will always remain in the dissociated form. Whenever you are adding HCl to water, it will always remain in this dissociated form. This is the ball and stick model. This is H, this is Cl, and here 3 white part, which is basically for hydrogen, H3O plus, and all these are negatively charged because these are nothing but Cl minus. Okay. Now we will see after preparation what are the physical properties of HCl. This is colorless, pungent, smelling gas. That means just like chlorine, this is also pungent smelling. Okay. So HCl is under normal condition, it is gas, Normally when we say HCl, what at a first glance it seems that it is liquid, but the liquid that you see in the laboratory, that is nothing but its water solution. Actually it is gaseous. It can be liquefied to colorless liquid when it is below boiling point, that is 189 Kelvin, or it can be converted to solid, that is freezes to white crystalline solid. This is the freezing point, that is melting point. Water solubility is very good. So that is the reason an aqueous solution of HCl is what we know as hydrochloric acid. So the hydrochloric acid that you see in the laboratory, that is nothing but the aqueous solution of HCl, which is basically containing, that you have seen in the last slide, two types of ion, H3O plus, Cl minus. Okay. Now chemical properties. As it is acid, it can decompose salts of weaker acid. So there are some acids which are obviously weaker compared to HCl. For example, sodium, H2CO3, carbonic acid, this is weak acid. Then it may be H2SO3. H2SO4 is strong acid, but H2SO3 is sulfurous acid, that is weak acid. So these two are weaker acid compared to HCl. So that is why when you have taken the salt of this weaker acid, now salt of H2CO3 means what? Just replace the H with some metal, you will get the corresponding salt. Now there are two replaceable hydrogen, right? So you can get two different types of salt. You can have NaHCO3, that is sodium bicarbonate, and if you are replacing both the hydrogen, now it is Na2CO3. So these are the salts of weaker acid H2CO3, that is carbonate and hydrogen carbonate, or you can also call bicarbonate. When HCl is reacting with this, what will happen? Now this CO3, it will be removed in the form of carbon dioxide and NaCl, water will be generated. Similarly, if you have taken the bicarbonate, then also same rules. And if you take the sodium salt of H2SO3, that is Na2SO3, sodium sulfite, then also see similar type of reaction. Here you have obtained carbon dioxide gas, but now you are getting sulfur dioxide because you have taken Na2SO3. These two you can consider as if analog. Okay. So same type of products. So this is the decomposition of the salt of weaker acid by the strong acid HCl. Fine. Reaction with ammonia. In presence of ammonia, HCl will be converted to NH4Cl. That is NH4 plus Cl minus. So basically ammonia is taking one hydrogen because it is base, acid base reaction, and it is forming this salt. So this is ammonia, this is HCl. So when we are adding ammonia, there is fume, and this fume is nothing but NH4Cl. So if there is some unknown gas, and if you are you want to prove whether it is ammonia or not, then you can perform this experiment, because this type of fume generation is possible only in presence of ammonia and HCl. Okay, so any one of these compound is unknown. Suppose you do not know there is some gas, whether it is ammonia or not, and it is here, it is, we are pouring it, so it is nothing but NH4OH, that is water solution of ammonia, which is also basically source of ammonia. So if you want to prove any gas whether it is HCl or not, then you can take ammonia solution NH4OH, and you can also do the reverse reaction. That is, if HCl is known, but another one, whether it is NH3 or not, that you do not. Okay. Application of this molecule, that is hydrochloric acid. Production of glucose and cane sugar, starting from starch. Refining of cane sugar, making glue and gelatin. So there is not much things to discuss. Okay, just go through these points. Here we have a problem. Reaction of KMnO4 and HCl. It will produce, that is, what will happen? See, four different options are there. Is it oxidation of Mn in KMnO4? and production of chlorine, reduction of Mn in KMnO4. Then again these two are repeated. Oxidation, reduction, two possibilities are there. And in options, that is the second part, it is either production of chlorine or production of hydrogen. Now we know that KMnO4, it is a very strong oxidizing agent, right? Strong oxidizing agent. That means oxidation of manganese is not possible. Because when we are saying that KMnO4 is strong oxidizing in nature, it means here Mn will gain electron. So Mn will be reduced, not oxidized. Mn will oxidize some other species, but itself will be reduced. So that is why oxidation of oxidation of manganese, that is not possible. These two not possible. It must be reduction of Mn. And when reduction of Mn is taking place, KMnO4, oxidation state of manganese is +7 here. And if it is reduced, that means here ACl, which is containing Cl minus, now Cl minus will be oxidized to chlorine, that is 0 oxidation state. So here production of chlorine should be the correct one, not production of H2. Now look at this. KMnO4 reacting with ACl. Though here we have balanced equation, but even without balancing also you can understand which option will be correct. So from +7, now after reduction it is +2, and Cl from -1, now it is 0. Though there is another product which is -1, but if you consider this is oxidation, this is reduction. So even without knowing the balanced equation, just apply the basic knowledge, that is KMnO4 is very strong oxidizing agent. So Mn from +7 state, it must be some in reduced state from +7 to +2. And ACl, where oxidation state of chlorine, it is -1. It must be losing electron and converted to chlorine. So here hydrogen gas cannot be produced. These two are not correct. So we have already cancelled A and C. Now among B and D, we are now cancelling B. So which option is left? It is option D. Here we are having reduction of manganese from +7 to +2, and also production of chlorine gas. Fine. Any doubt? So this is the end of this group. Next we will start the next group. Okay. So this is the last group of P block elements that is in this chapter. Group 18. Noble gases are present here, or sometimes we also call inert gases, right? So here we have all the gases. See, from the color you can understand they are not metals, they are not metal alloys, they are non-metal. And here the last one, which is basically synthetic, that is radioactive. Members of group 18, if you consider modern periodic table, they are called noble gases. Now why they are called in this way? Because they have a tendency to be chemically inert, so that is why noble. Remember, no, there are some metals which are known as noble metal. For example, platinum. Why it is called noble metal? Because they are very non-reactive in nature. Not that is, under normal condition you cannot expect any reaction. So just like these noble metals, these gases are also highly non-reactive, so that is why they are called noble gases. Krypton and xenon, that is these two, they are fluoride compounds and also oxides, fluorides of krypton and xenon, and also oxides and oxyfluorides. All these are actually known. That means it is the compound of krypton, xenon with either fluorine or oxygen, or when both fluorine oxygen are present, it will be oxyfluoride. Okay. Now, if you are thinking that why only compounds with fluorine and oxygen we are getting, why not compounds with other elements? Because in the periodic table there are so many elements, right? Now the reason is fluorine and oxygen. These two are the most electronegative element in the periodic table. Now, as they are most electronegative, so they can easily remove electron from krypton and xenon. Okay, so that is why it is possible to get compounds of these two, because they are already very non-reactive. They hardly want to react. Okay, but still, if you want to get products with other element, it is normally product with fluorine and oxygen, because these two are the most electronegative. The preparation of these compounds can only be performed under extreme condition, because it is not very facile process. It is energy requiring process. So that is why extreme conditions are required. Extreme conditions means temperature, pressure, both these are very high. If we consider their occurrence, natural occurrence, they are inert in nature. So all these gases except Rn and Og, this is the full name. So except the last two, all these can occur in the atmosphere in the free state. And remember, they are monoatomic, okay, not diatomic. Their atmospheric abundance in dry air, it is around 1% by volume. So see, this is so small number, right? And in this 1%, there are different noble gases, but argon is the major constituent. Helium and sometimes neon, that is the first two elements, they are found in minerals of radioactive element. For example, pitch blende, monazite, cleveite. And helium is also present in natural gas, and the amount of helium is 2 to 7%. So if it is asked what is the source of helium, suppose there are some options given, so answer will be natural gas. So these are the occurrence, but we will see some more points related to occurrence. Xenon and Rn, they are rarest elements of the group. So see, in the group you have helium, neon, argon, krypton, xenon. Now the last two, except Og, the last two are these are rarest. Okay. Now Rn is radioactive, and it can be obtained as decay product of 226 Ra and 230 thorium. So this is radioactive. So whenever we will do the discussion of the elements in this particular group, you will hardly see compounds of Rn. Most of the discussion it will be up to xenon. Okay. And Og, it is synthetically produced. So here from these two equations you can understand 230 thorium, this is the mass number, this is the atomic number, and this is radioactive reaction. After conversion we are getting 226 Ra and helium. Okay, and now this 226 radium, if it is further there is some removal of alpha particle, so this is also, helium is also known as alpha particle. Alpha particle and gamma energy is reduced. Now Rn is generated. So see here, from thorium first there is generation of Ra, and then from Ra we are getting Ra. So this is basically the decay product of thorium and radium. Fine. Here we have calcium 48 and californium 249, and we are getting, after removal of 3 neutron, if it is escaped, then this organization 294 mass number, it can be produced. And see, this is so unstable. Half-life is 0.7 millisecond. Half-life means the time in which 50% will be, there will be disintegration. So the time is so low, which proves it is highly unstable. Okay. So is there any doubt in the occurrence? Next we'll start electronic configuration. So here if you add these two numbers, that is 249 and 48, 297. Okay, so the mass as it is maintained, left hand side, right hand side, mass should be 297, but as 3 neutron are escaping, that means it will be -3, that means 294. Okay, electronic configuration. Now as we have reached the right hand side extreme, it is fully filled configuration. In group 17, what you have seen, it is NH2NP5, but now it is NH2NP6. So all the elements here will have complete duplet and octet. So the term octet, you have heard it, that is 8 electron in the valence shell. But what is duplet? It is specifically for helium, because here octet is not possible. Maximum capacity is 2, so it is, this term is for helium. They do not have any inclination to form compounds because they are already satisfied with their configuration. So still, if you want them to take part in reaction, you have to provide very drastic condition, that is high temperature and pressure. Okay, so see, this is the general configuration NH2NP6. Now here NH2NP6 not possible, here you can have maximum NH2, but rest of the part, if you see, this is NH2NP2, NP6. So up to argon, there is no d electron, but when you are moving from argon to krypton, that is from third period to fourth period, now there is 10 3d electron. Then in case of next period, when you are jumping, now there are 4d 10 electron, and then in the sixth period, there is also presence of 14 F electron. Okay, and these are the atomic. Any doubt in the electronic configuration? Now some atomic properties of inert gases we will see. First is atomic radii. So these are the atomic radii of different inert gases in picometer, and in the x-axis we have all these gases, and here you can see it is increasing. So it is expected as we are moving down, the increase in atomic radii, gradual increase. But small thing that you have to notice here, the difference between neon and argon, if you consider, it is around 120, 160. Neon and argon 160, 190, that means it is around 30. Okay, but the next difference, it is 10, this is 20. So gradually the difference is decreasing, and we know this is this type of trend you have already seen in case of other group members. So what is the reason behind it? It is the presence of d and f electrons as we are moving down. So that is the reason we are getting this type of ionization energy. Ionization energies are given in kilojoule per mole unit. Okay, maximum ionization energy, it is for helium, and that is a normal observation for any group, right? So as we are moving down, the valence shell electron, it is the distance with nucleus, it is increasing. That means you can easily remove the last electron. So that is why ionization energy is decreasing down the group. Okay, now for these two, as ionization energy is very high, you will hardly see that helium and neon, there is no compound of these two elements till now reported. Why it is so? Because if these two, they are taking part in reaction, you have to provide this energy, which is very high. So that is why their compounds are not. And mostly compounds of xenon are common. Why it is so? Because if you compare up to this, suppose just forget about Rn. If it is up to xenon, this is the lowest ionization energy. So it will be easier for xenon to take part in reaction. But why we are not considering Rn? Because it is radioactive in nature. So as it is radioactive, so that is why its compounds, they will be highly unstable. So that is why the compounds of xenon are most common. Now, because of their closed electronic configuration, they have high ionization energy. That is, in general, their ionization energy value is very high. See, all these are having 4 figure, 2372 up to 1037. All these are actually very high. Yes, it is true that among them, helium is having maximum. But if you compare ionization energy with other groups, here it is maximum because it is fully filled stable configuration. And this is the graph. See, this difference is very high. That is the difference between this is 1, 2, 3, 4. Okay, this difference is very high, as you can see. But after that, the difference is gradually decreasing, and it is the same reason, presence of d and f electrons. Electron gain enthalpy. Now, electron gain enthalpy we have seen in case of group 17 elements, that is for halogens, and there what you have seen, it is mostly negative. No, not mostly, all the values are actually negative, and chlorine is having maximum electron gain enthalpy. But now look at the values, all are positive, and it is expected because as their electronic configuration is closed configuration, it is fully filled stable configuration. So when you are trying to add extra electron forcefully, it is not facile process. So it cannot be exothermic reaction. It must be endothermic, and that is why positive sign is there. So it has no tendency to gain electron. That is why electron gain enthalpy, the values are highly positive. Okay. Any doubt in these 3 atomic properties? Atomic radii, electron gain enthalpy, ionization energy. Physical properties, that is melting point, boiling point, density, all these. These elements are colorless, tasteless, odorless, and water solubility is also not good. And if we see their melting and boiling points, they are very, very low. So mostly what we say, they are noble gases. That means under normal condition, they are gas. So obviously their melting point and boiling point will be very low. And actual reason why it is so, because the only type of interatomic interaction that is possible in these elements is weak van der Waals force, because they remain as monoatomic gases. So suppose just take argon. It is atom. It is fully satisfied because configuration NH2NP6. Another argon. Now you cannot expect any polarity generation between 2 argon atoms, right? So dipole interaction is not possible. Maximum what you can do, van der Waals force. Now van der Waals force means, suppose this is argon atom and electrons are equally distributed, but in some, suppose at a particular time, positive charge, that is electrons are on one side, so positive charge will be on other side, and another argon. Now if it is facing the first atom, now if positive charge in the left hand side, negative charge in the right hand side, now under this that is, it is as if instantaneous generation of charge. It is not permanent because electrons are symmetrically distributed. But suppose at a particular time, just for a fraction of second, the electron distribution, it becomes unsymmetrical. Under that condition, if 2 argon atoms are in this orientation, then there will be some interaction. But see, this is very weak interaction because it will happen hardly. Now, as this interaction is very weak, so that is the reason they remain in gaseous form. So their melting point, boiling point, if you see at the values, all are negative. That means very, very low, right? Melting point, boiling point increase on descending the groups. See, when you are moving down, the values, though negative, but still it is increasing. And that is expected because of increasing magnitude of atomic mass, and when mass is increasing, van der Waals force also increasing. Due to these forces, noble gas can be liquefied at very low temperature. And when you are moving down the group, the ease of liquefaction of noble gases will increase. That means you can easily liquefy them. And that is expected because suppose if you want to liquefy xenon, you just have to reach this temperature. But if you want to liquefy helium, Now you have to reach much more negative temperature. So that is, it is difficult. Helium has the lowest boiling point, that is minus 268.83. If you convert to Kelvin unit, it is 4.2. And see, it is the lowest boiling point of any known substance. Okay, so you can understand how low it is. And here we also have this boiling point versus all these gases. The gases are in the y-axis, boiling point in the x-axis. So see how it is changing. Now, chemical properties. So they are chemically inert, that you already know, because their configuration is already closed. And their ionization enthalpy is very high. Electron gain enthalpy, that is also highly positive. It means that removal of electron, ionization enthalpy high, that means removal of electron is difficult. Similarly, electron gain enthalpy, as it is positive, gain of electron is also difficult. So both the processes are difficult, then how it will take part in reaction? Okay, so that is why their compounds are very rare. And how the first compound of inert gases are discovered? Neil Bartlett was the first to prepare a compound of xenon. So this is the first reported compound, and it is xenon hexafluoridoplatinate, this molecule. Though later many compounds of xenon are synthesized, that is they are compound of xenon with when it is reacting with fluorine, oxygen, and both oxygen and fluorine, FO and both F plus O. So mostly these two will react with inert gases because these two are the most electronegative elements in the whole periodic table. They can easily remove electron. That is, when it is forming, there is formation of xenon fluorine bond. Obviously fluorine is more negative, so negative end will be this, and this will be the positive end. Now positive end means what? Xenon must have lost some electron. That means ionization enthalpy we have to provide. Now as fluorine is highly electronegative, it can draw electron easily from xenon. So that is why, though ionization enthalpy is very high, but still this bond formation is possible. But instead of taking F, if you have taken any other element which is not having very high electronegativity, then bond formation will be difficult. Okay, so that is why compounds of xenon are known, and that is mostly compound with oxygen fluorine and both oxygen fluorine. Chemical reactivity increases with a decrease in ionization enthalpy down the group, and that is why the compounds of xenon are most common. And after xenon there is radon also, but as it is radioactive we do not consider it. Now compared to xenon, compounds of krypton are fewer. Only this one is known and studied in detail. Then ionization enthalpy of the first three, that is helium, neon, argon, they are so high that they cannot form any compound. In spite of having lesser ionization enthalpy than xenon, argon also form, see, only some compounds, that is lesser than xenon, and some complexes, because radon has no stable isotope because it is radioactive. Now, though this question I have already discussed, here for your convenience I have also added all the values of ionization enthalpy. All these are ionization enthalpy in kilojoule per mole. So this question I have already given the answer, that why xenon compounds are more stable than those of other noble gases. That is why you do not get compound of helium, neon, argon, krypton, xenon, and then radon. This is the element where maximum stable compounds are formed. So the reason is here ionization energy minimum among all these. But Rn is having lesser ionization enthalpy than xenon, but still Rn compounds are rarer compared to xenon because it is radioactive. So this is the answer of this question. Okay, any doubt? Another question we have. This is also the question I have already answered. That is why most of the noble gas compounds are forming compounds with fluorine and oxygen, and the reason is its high electronegativity. Xenon fluoride compounds. Xenon can form 3 different binary fluoride. The word binary means compound of 2 elements, xenon and fluorine here, by direct reaction of elements under appropriate experimental condition. So depending on what type of condition you have taken, you can get 3 different fluoride. This is 2:1 mixture, 673 Kelvin, 1 bar. Then 1:5 mixture. Now the ratio is changed, temperature changed, pressure changed. And when it is 1:20, now amount of fluorine is very high. Temperature, it is lesser than the first two, but pressure is very high. Now you are getting xenon hexafluoride. Xenon hexafluoride can also be obtained by reaction of xenon tetrafluoride, that is XeF4, when it is reacting with O2F2 at 143. All the fluorides of xenon are white crystalline solid. They are strong oxidizing in nature, and they can also serve as fluorinating agent. That means they can supply fluorine atoms. Example of fluorination reaction. You are using XeF4 to supply fluorine to these compounds. SF4. Now after gaining fluorine, it is converted to SF6. PT is accepting fluorine, it is now PTF4. And benzene, it is accepting fluorine, now it is fluorobenzene. That is fluorine attached to aromatic. So see, in these reactions, though we are saying it is fluorination, but these are also one kind of oxidation, because whenever there will be fluorination, oxidation will also happen. SF4 oxidation state +4, now it is +6. It is 0, now it is +4. Okay, so simultaneously it is acting as fluorinating agent as well as oxidation also. Some oxidation reaction, XeF2 reacting with HCl, now it is converted to chlorine from -1 to 0, and xenon from +2 oxidation state, now after gaining electron it is having oxidation state 0. Then XeF4 reaction with Ki iodide is converted to 0, that means loss of electron. Xenon is reduced to 0 from +4 oxidation state. And the last one, again XeF2 reaction with BrO3. Bromine is having +6 oxidation state, but now it is +8 oxidation state. So this is also oxidation. How they react with hydrogen? XeF2 reaction with hydrogen. Different, that is products are same. Okay, here actually amount, depending on what amount you have taken, different number of moles are obtained, but product is same, that is hydrogen fluoride and zinc. Some more discussion we will do which is related to xenon fluoride, but today we don't have time. So is there any doubt regarding all the slides in today's class? Okay, so we are ending the session here. Thank you for listening.